All right, well, welcome to Friday the 13th. It's been that kind of day so far, so we'll see if it continues to be that way in class today. Our plan today, I want to show you just a little bit more with Green's theorem. Specifically, I want to show you how we deal with regions that are not simply connected, because there's a nice little workaround for that, which can be really, really useful when you've got functions that have bad spots, basically. So I want to show you that, and then we're going to talk about a couple of properties of vector fields. There's this thing called divergence and another thing called curl. So we'll look at how we calculate those, what they mean, because that's kind of setting us up for later things. But yes, as always, I'm more than happy to look at homework questions, and I see that Victor jumped in. He said that he'd like to look at number 5 from 6.4, and Seamus is all on board with you there, Victor. So we can definitely look at that. So let me just go and write that down. Any others that we want to look at? All righty, well, then let me get that homework pulled up and we'll switch over and we'll see what we can do about it. All right. Trying to think if I've heard any good jokes lately, but I haven't. Anybody want to share a joke while we're waiting? All right, that's fine.
I think I got one.
Oh, okay, go for it.
What rock group has 5 men that don't sing?
What rock group?
Mount Rushmore.
If you're going to use that one, go with 4 men.
Is it
Just saying.
4?
Yeah, there's only 4 presidents on there.
Oh,
But
well, whatever.
see, that's what threw me. If it had been 4, I'd have gotten it. I was kidding. All right, so let's take a look. So here's number 5 from 6.4. We definitely stalled long enough. So it says C is a circle of radius 3 centered at the point 0, 4. And we want to evaluate the line integral over that path of 7y minus e to the sine x dx plus 9x minus sine y cubed plus y dy. All right, so it's just a typical kind of line integral problem. We've got a function we've been told to curve, and we want to find that integral. All right, so let me go ahead and write this down so that I've got it handy. So let's think about what our options are here. We could start by parameterizing the curve, right? I mean, it's just a circle after all. Yes, it's centered at 0, 4, but yeah, whatever. But we can still parameterize it. And once we've got that parameterization, we could plug in for the y's and the x's, also the dy's and the dx's. So we've got it in terms of t, and then integrate as we go around that circle. We probably would make our bounds like 0 to 2 pi, I'm going to guess, since we're doing a circle, right? So we could just slug it out. However, since it's a closed curve and the region that it encloses is a simply connected region, it's just a circle, alternatively, we can use Green's theorem. And that's what I'm going to want to do here, regardless of the fact that they told us, coming from section 6.4. This is definitely one we want to at least consider, Green's theorem. So let me pull up the whiteboard so we can work this sucker out. All right, so let me just rewrite that integral here real quick. So 7y minus e sine of x dx. And we got this guy. Okay, so if we're going to do Green's theorem, let's remember what we have to do. We want to turn it into a double integral over the enclosed region. And then what is it that goes in here? What do we actually integrate? And I'll take it in either form if you want to go with the book form or the form that I tend to give you because I bounce around all the time. Okay, so Victor just put in the chat box that it's qx minus py. So we need qx minus py, and then that's going to be dA. Okay, so Q and P, those are the components of the field, right? Because the field in this case is P comma Q. If you are using my notation that I slip into, this would be NX minus MY. All right, so far so good. So now is what are P and Q? Because we're not given it, right? We're not given an F equals. So I'm curious if anybody has caught how you can get P and Q from this form.
The
P
partial
is whatever for
derivatives.
dx, Q is for whatever's for dy.
Yeah, so this right here is P, and all of that is Q. So this is called the I think it's called the differential form. I know that I think I mentioned it last time we had something that was in differential form and I changed it to the other form or something like that. And I just was like, oh yeah, this is differential form. Hopefully you spotted it in the book. It's another way of writing what we get when you do the F dotted with T. So this then should be nice and quick, at least figuring out what we're integrating. So we need QX, which is 9. And then we need to subtract PY, which is 7. So this is the double integral of 2 dA. So by Green's theorem, instead of doing it as a line integral, we can do it as a double integral of 2 dA. All right, so now let's look at what that region is. So we were told it was a circle that was centered at 0, 4 with a radius of 3. So it's like up here. So we need to do the double integral over that. All right, so at this point, what do you want to do?
Polar.
Okay, so polar's jumping out on you. Bradley, you just said it. Victor typed it. Polar would not be bad for this region because it's a circle. However, that is not what I want to do. I want to be a little bit lazier. Anybody recognize what I do? What if I were to rewrite it as 2 double integral of RdA? Is that?
So just 2 times the area of that circle.
Yes, sir. It's just going to be 2 times the area that's enclosed. Well, it is a circle, so it needs to be pi r. R, I believe, was 3. So the value of that double integral is going to be 18 pi. And this is when you guys all mutter under your breath and shake your heads and shake your fist at me. It's like, yep, gotta love those little tricks. And I know I mentioned it before, and I'll mention it again. Whenever you have a constant, keep in mind this trick because it's way faster. Yeah, we could have turned this into polar and done the whole conversion and that, yeah. And that would have been better than trying to do it in rectangular. But yeah, let's just be quick about it. All right, so the value of this line integral is actually just 18 pi. And look at how much easier green made that. I mean, I don't like using the word trivial a lot, but this one, it pretty much made it trivial, right? Think about what we ended up having to do once we did Green's theorem. I mean, yeah, we had to take some derivatives, but they were easy derivatives. And then the integral was you don't even have to integrate kind of integral, which doesn't always happen, right? Yes, I'll admit that doesn't always happen, but when it does, it's crazy fast. All right, so how are we feeling about it? I'm gonna go get the points. I haven't earned any homework points in a long time. So they said we already have our pi, so I only need to put an 18 here. So submit my question. Yes, green check mark. Anyway, this is why we like Green's theorem, because it takes horrible line integrals and can make them really easy double integrals sometimes. All right, so is it better for that one? For those of you guys who wanted to see it? Good. Any other homework questions before we turn this off? All righty. I will stop sharing that. Cool. All right, well then I'm gonna hop up to the whiteboard, you guys, in just 1 second. All right, hold on. I'm back. Victor typed something in the chat box. Let me see what it says here. So how can we recognize when it's better to go from a line integral to a double or a double integral to a line with Green's theorem? Okay, that's a very good question, and it's a legit question. Think about the one that we were just looking at. Something that made me go, I really don't want to do that as a line integral was just how horrible P and Q were. If you go back and you look at those, right, like we had a e to the sine of x, and there was like a sine of y cubed plus y or something like that. Any kind of parameterization, like literally any, even if it's just x equals t or y equals t or whatever, even something that simple is going to make that thing really ugly to integrate, right? Like try integrating e to the sine t. It's not going to be pretty. So a lot of the time, if your field is such that it's pretty gnarly looking, it's worth at least checking. So what I do, because it's not always obvious is the problem. It's not like you can just necessarily look at P and Q and go, oh yeah, if I take those partials and then do Green's theorem, it'll be a nice simple double integral. Like this one, it actually is. Looking at it, you can see the derivative of the first one with respect to y is easy. The second one with respect to x, also easy, right? So sometimes you can see it that way. But what I do is I go ahead and I find the partials. I immediately go and I try to find p, the way this is done, py, yeah. So py and qx. I look at those right away. And really the reason is I'm looking to see, is it conservative? because that's the best case, right? Like what would have happened if this had been a conservative field?
F of B minus F of A, boom, boom.
Okay, and even better, since this was a circle, what do I know?
Should be 0, right?
0.
It's just 0. Yeah, so to me, it's always worth looking at those two partials to see if I get 0, right? Such that it's a conservative field, that those things are equal, then I'm done. Okay, well, since I'm going to do that to check anyway, I'm already getting those partials. I'm already seeing py, I'm already seeing qx. So I'm going to be able to leave me with, right? So at that point, if those two things look ugly, right? When I do that subtraction, I look at that double integral and I go, maybe not. Then I'll reassess and I'll go back to the line integral and consider, well, what's it going to look like if I do my parameterization, right? So really that's my answer to you, Victor, of the how do I recognize going from line integral to double integral, when to do that is, well, I'm going to check for conservative anyway. So I already have the partials and I look at the form of those partials and see. And like in this case, oh, the partials were, what were they, 9 and 7 or whatever? Oh, I am super excited. Constant partials mean just multiply by area, right? Now, it could be that the curve is not so nice though, right? Like this curve was perfect for me to do a area thing because it was a circle, right? It enclosed the circle, its area is super easy, and I'm done. But you can imagine that it could be a shape that's not quite that nice. Well, that's something else then I would take into account. But if it's not very nice, it's probably hard to parameterize unless the already given. And if the parameterization was already given because the curve is kind of gnarly, Green's theorem may not help all that much, right? Because for Green's theorem, we need to basically get rid of the parameterization so they figure out what the shape is to do a double integral. So there's that part of it too. If the curve is gnarly, but a parameterization is given, you probably don't want to go to Green's theorem because it's probably not as easy to describe that curve in terms of rectangular stuff or even polar if we're lucky. So it's not that simple of a question to answer, and a lot of it is, adjusting on the fly, kind of like we're used to seeing in other arenas in calculus, right? Where it's which method do you use? Depends what I've got. So then the second half of that, when you're saying you use the double integral to a line integral. So like we saw that example, or I showed you an example of finding the area of the ellipse that way, right? Really going to a line integral from a double integral, you're going to want to do that if there's a easy parameterization. If it's really easy to parameterize your double integral, but you also have to be able to find a field whose components are such that when you do that mixed partial thing, right, the py, I always forget. It's pq, yeah, so py minus qx. You have to be able to create a field so that py minus qx is actually what you're integrating. And so that can be challenging as well. I find that trying to go from a double integral to a line integral is more difficult in general. But the only time I'm going to try to do it is if my region is such that it's easily parameterizable. I can describe that curve easily. And I can kind of go backwards to find a field that gives me my integrand. The good news about that is that you can pretty much do it however you need to make it so that you get the integrand. And that's kind of what I was showing you with the area example, right? We did this to find the area of the ellipse where we went from a double integral to a line integral. And I just went with a field that was, what was it again? It was x, no, y over 2 comma x over 2, I think is what it was. And just because that's the one that ended up working really well, even though we could have done y comma 0 or 0 comma x, or right, like there are all kinds of different options for that. But having options is kind of nice in that regard. So maybe I answered your question, maybe I just confused things more, but the real moral to that story is it just depends. It depends on what you're given, and there is no good always do this. But I can say if you're doing a line integral, always a closed line integral. Well, no, line integrals at all. Always check to see if your field is conservative. Always. It's usually a fast check. And if your field is conservative, it's going to be so much easier to either use the fundamental theorem or just go 0 because it's closed. That's going to be way easier always. All right, so is that kind of good, Victor? Did I talk long enough to make you go, just shut up and let's move on? All right. Any other questions before I hop up to the whiteboard? And thanks for asking that, by the way. Sorry, I almost ran away with that answer. Okay. So now I am going to hop to the whiteboard, and I will be back with you guys in just 1 second. All right. So hopefully you're starting to see the benefits of Green's theorem and seeing that it's worth doing, definitely, certain situations. Okay, but there are definitely some restrictions to Green's theorem, and the most important one is the fact that it needs to be a simply connected region. So we can't have any kind of a hole in our region or anything like that. And we'd really like to get around that. I'll show you an example in a little bit of why that's super useful. But what if we had, instead of just like a circular region, what if we had a circular region with a hole cut out? All right, so we're looking at a washer or a donut or however you want to describe it. So there really are two curves that are boundaries of this region, right? So even if we wanted to go with positive orientation, we'd have out here a curve, say, call it C1. And then we'd have on the inside another curve that would be the curve C2. Now, C2, I'm actually going to have it go in the other direction. And if you go, but wait a minute, Bruce, you said we always wanted to do this counterclockwise, and the interior one is actually clockwise. What I'm going to say is, well, I really want it to be positively oriented, and positive orientation meant that the interior of our region, or region itself, was actually always to the left of where we were. And so you can imagine if what we're looking at is this washer area, in order for it to be to the left of us as we're walking around C2, we'd actually have to walk around C2 backwards, because it's not the interior of C2, it's the exterior of C2 that's our region. So I'm just going to make it so that I've got positive orientation for both. Well, that's all great and everything, but the problem is it's still not a simply connected region. All right, so you're going to love this workaround. So here's what we're going to do. I'm going to put in another curve. I'm actually going to put in 2 more curves. Well, technically 4 more curves. So here's one of the curves I'm going to put in. I'm going to put in just a linear curve right here. And I'm going to give it orientation that's going to the right. But at the same time, I'm going to put another curve that's exactly the same curve. I'm going to show a little bit of separation, but they're really the same line. But this one's going to be going the other direction. Okay, now imagine that we're doing a line integral over all of the curves here, right? So we're just doing a line integral. What did I actually do to the line integral by putting in those 2 curves?
An entrance and an exit.
Okay, so we've got an entrance and an exit. Let's say, I mean, I'm actually like connecting the 2 curves now. But also think about it this way. As I use that one on the red, I'm going to get some value for line integral, right? It's whatever I get when I go on the red. When I do the blue, since I go in the opposite direction, I'm going to get the opposite value. And so if I add those 2 together, the end result, and this is like Victor just put in the chat, the end result is nothing. In essence, I just added 0. Okay, so I added 0 to the line integral. Okay, big deal. Well, here's the big deal. Now I want you to look at what the region looks like. So let's call those, say, C3 and C4 for those 2 curves. So let me redraw the picture, and I'm going to exaggerate just a little bit so that you can actually see what's going on. But now what I've got looks like this. And
Honestly,
I like
that's
how
pretty good. C, man. That looks
I know,
good.
right? It's almost like I'm drawing a Colorado flag or something. Like gold in here. Anyway, so yeah, so now it basically looks like a C, but like Seamus said, it's sort of like I gave an entrance and an exit in. But look at this region now. Is that simply connected?
Yeah.
Yeah, it's a simply connected region now. There are no holes, there's nothing in there. It's all one big region. It's a weird shape. I mean, it's not like we think of them, but it's all in one piece. There are no holes inside of it. So now I could apply Green's theorem. I could apply Green's theorem to this entire chunk, just realizing now my line integral, if I was going to do it as a line integral, would have 4 pieces to it. And even better, check out the orientation. So on the outside, we were going around in a counterclockwise direction as we needed to. On the inside, we were going around clockwise. And on these 2 cuts, one of them is moving to the right, and the other one is moving to the left. And if you look at what we're doing on the boundary now, on the entirety of the boundary, we're moving in a counterclockwise direction. Okay, so you can play tricks like this and still make it so that you can apply Green's theorem. And granted, I know this is the kind of thing that makes you guys hate mathematicians. Well, maybe you guys not anymore because you're getting kind of advanced, but these are the kinds of tricks that make other people go, you goddamn mathematicians just pull shit out of your ass and do whatever you want to make it work. Yeah, we do. Totally. but we do things that are not illegal. We just think outside the box, right? I mean, I didn't do anything. I didn't change anything. I added 2 lines, but those line segments give me opposite integrals so that in the end I get 0. But I did it in such a way that now I can apply what I want to apply. So while it makes other people hate us, this is one of the things that makes me proud of being a mathematician. It's like, oh yeah, hell yeah. Come up with this stuff all the time. Figure these end arounds. All right, so the moral of the story here is that even if you have a region that's not simply connected, if it has a finite number of holes like this, you're good. Because like, what if there was a second hole? What would I have to do?
The same thing again?
Yeah, same thing. Just make sure I have a couple of, in and outs to the other hole. I've got 20 holes. Okay, well, I'm going to have 20 of these little line segments that are countered by another 20 of the line segments that in the end don't do any different. All right, so it's a great little trick. It's also especially good if we run into a field kind of like the one that you guys just asked me about on that homework. Because imagine that we had that exact same field, right? The one whose partials ended up giving us 9 and 7. So let's say we had done the same thing. And instead of worrying about the line integral, we looked at it as the double integral. Okay, well, now I'm integrating 2 over this shape. Well, what's the area of that C? Remembering that that C is really, they're connected. Well, it's going to be the area of the bigger circle minus the area of the smaller circle. Calculate that and multiply by 2, and I'm done. Right? So just be aware that there are ways of getting around some of the issues, and this is one of the big ones. If it's not simply connected, you can do this. Anyway, so watch out for that trick. All right, cool-ish.
So I have a question. I know there's not really a gap in between them.
Right.
So is that like a differential chunk?
Yeah, if you want to think about it that way, yeah, this gap right here is infinitesimally small. To the point where they're not really different. But if you think about what we're trying to do when we're talking about a region that's not connected, we basically have eliminated the points on that line. And as soon as we eliminate points on a line, it's no longer a donut. There is that gap. It's 0 width gap, right? A line has no width, but there's still a gap so that it's split. I just have to exaggerate it so you can actually see what's going on. If you could zoom in close enough, which you can't because infinitesimally thin, right? But if you could zoom in close enough, this is what you would see. Does that make sense?
Yeah.
Okay. And did that actually answer your question? Maybe the more important thing.
Sort of. I was just curious because it's so tiny, it made me think of a differential chunk. Would we have to input that in as well, or no?
When you say input that, do you mean like take that away from the area, for example?
I guess, or like put it into our integral, or
Okay. So the putting it into the integral, no, you don't have to, like, that has no bearing on anything that's actually in the integral. If we had one of these where we were going to create so we're going to a double integral, and you want to describe this region, technically you would be subtracting it off. But when you go to integrals, remember you take a limit as you go to 0 anyway. Well, that thing's going to go to 0. The amount you're taking off goes to 0. And so the end result is it's exactly the same as if it wasn't there. And we've played that kind of trick, trying to think like the most recent time. I think we saw that a little bit of that when we were doing the area, when we tried to find a little differential chunk of area for polar, and I did it geometrically, you may remember that we ended up with something like a dr squared. And I made that argument of, well, that dr squared, we can just ignore it. Because dr is already so small that when we square it, it's hella small. So just ignore it. I don't know if you remember that, but we play that kind of trick all the time. And that's sort of the same situation here. Technically, yeah, there is no gap, technically. But yeah, there is a gap. It's just infinitesimally small, and we can ignore it. So
I can roll with it.
okay. I figured if I kept talking, I'd bully you enough just to go, yeah, sounds good. I'm just a big bully. All right, so feeling all right about that, kind of? Now, let me explain why we need this. Like, it's not just a, yeah, it's kind of nice, but it's a, no, we need to do this at times. Take, for example, let's say we had some sort of a field that had a problem at the origin, right? Like isn't actually defined at the origin. I'm going to make one up, and this is troubling because it probably means what I'm going to do is something that we can't actually differentiate or something. But let's say that our field was given by this. No, let's make those squareds. Okay, so let's say our field is x over x squared plus y squared and y over x squared plus y squared. So that field is defined everywhere except for the origin. Yeah.
Yeah.
So anywhere else is fine, but the origin's a problem. So then suppose I said, okay, well, I want to do a line integral that includes the origin. So I tried to make sure it's definitely not a circle or anything. That's why I made it. This isn't me just having trouble drawing circles. All right, let's just make sure it's definitely not a circle, but it's a closed path that goes around the origin. And I want, let's say, just the integral over the curve of f dot of TDS. Okay, now I can do that as long as I can parameterize my curve. I can take that and I can dot it, and and with the f, and I can do it, right? But the problem is I can't use Green's theorem because of the fact that there's an issue here at 0, 0. I don't know if you remember all of the things that we needed for Green's theorem, because there was like that kind of like that whole big if this and that and right. But in there was that we had to have continuous second partials in the entire region. And that's the problem we have here. You take partial derivatives of those guys, they're not defined everywhere in this region. If we weren't in this region, right, like if we weren't in this region, or if 0, 0 wasn't in that region, we'd be fine. If instead this was my curve, I'm good to go. I can use Green's theorem, it's totally fine. Because there isn't a problem spot in that region. But the one that I drew here, there is an issue. Okay, so here's what we do as a end around. We introduce another curve. And we're going to pick a nice curve that also contains that 0. All right, now if I use this as my other curve oriented the other way, we're now back into this exact same kind of picture that I showed you. Which means we can apply Green's theorem to this region that now doesn't contain 0, 0, because the partials of those are all fine, no big deal. And what we know, if we call these guys, if this is our C that we were trying to find the integral around, call this one, say, C1. I know that with Green's theorem, I'm going to get actually like the difference in the two. So that whatever I end up getting from my Green's theorem on this, the double integral over the region, this is going to be the line integral of C minus the line integral over C1. And the reason it's a minus C1 is because the fact it's going in the opposite direction for the interior part. So basically what this is going to let me do is find the integral on C by doing the double integral over the region that now misses the problem spot, and add to it the line integral C1. And we still have the same issue that like C1, I can't use Green's theorem. But if I make this a nice shape, if I make C1 a good curve, something that's easy to parameterize or whatever, then I can actually do that line integral simply. So it takes a line integral that's basically impossible to do, and trading it out for a line integral that we can do, and adding to it double integral over the region. Let's see. Let's actually see what this would look like. I have no idea what the partials of this are going to be. So actually, I have an idea. I think we got lucky, but let's just see what happens. So let's see if we can answer this question. Figure out what the line integral would be going along C. So I'm going to start with my usual, which is let's take the partials and see if it's conservative. And if it's not conservative, well, we'll still take the difference of them and we'll use Green's theorem there. All right, so Py, the derivative of this with respect to y, the x is a constant, the x squared plus y squared, that's to the -1, so we're going to get a minus that thing squared times the derivative of what's inside, which is 2y. Oh yeah, no, this is nicely. That's all right. Okay, so there's my Py. My Qx, same kind of deal, except we're going to get a y times x squared plus y squared to the -2 with a -1 on that times the derivative is 2x. Oh no, actually this is perfect. Nice. I guess Friday the 13th is not so bad after all. Okay, so check it out. I've got Py equals Qx. So what do I know? All right, so this guy's conservative.
Wait, they equal each other?
Yep.
Is piece of y, is the denominator a piece of y to the -2? Oh.
Sorry, they're both supposed to be +2.
Okay.
I mean, I don't know what you're talking about, Seamus. They're identical. Look. Get your eyes checked, dude.
Yeah, my bad.
No, yeah, sorry about that. All right, so since they're equal, this is conservative. Well, that's actually really awesome. Because that tells me that this piece right here equals 0. because for that region that's missing the middle chunk, right? Remember, that's what this double integral over R is. It's the region that doesn't include that middle chunk. I can apply Green's theorem. Green's theorem, when you have a conservative field, just tells you that's equal to 0. So that means that C and C1 have to have the same value, just different signs, right? Or if I've got C1 set the way I've got it going, we're good to go. All right, so let's see if we can find the integral for C1. Now, I need to have this going clockwise. And we're really not used to doing it clockwise. We're used to doing it counterclockwise. So what I'm going to do is I'm just going to make it the negative of C2, where C2 equals C1 but counterclockwise. That way we don't have to worry about trying to do a different parameterization. We'll just do what we normally do. We'll just throw a minus sign on it. All right, and so that's what the integral over C is going to equal. Since C has to equal C1 because of the fact that the double integral was 0. If I just calculate the usual unit circle going around here, then I know that the opposite of that is what C is going to equal. All right, well, let's try it. All right, so parameterization for the unit circle. We've got R is equal to cosine t sine t. So R prime is minus sine t cosine t, which means the integral over that circle of f dot r prime dt, well, that's going to be integral from 0 to 2 pi. If I dot f with r prime and I put in my other values, I'm going to get cosine times minus sine. So minus sine cosine over 1, because that's what x squared plus y squared is going to equal. The other one, if I do y, I get sine times cosine, so plus sine t cosine t, also over 1. All right, well, that's the integral of 0 which is 0. So I didn't use Green's theorem on that little circle because I couldn't use Green's theorem. I just did it the old-fashioned line integral way. But now that tells me what's going on with that other curve that's going around it. So what was the line integral of the original curve I drew? What's the value of that line integral with this field? Yeah, it's 0. 0 equals 0 equals negative 0. They're all 0. So I couldn't use Green's theorem originally. But by introducing that other loop on the inside, I could use Green's theorem. And there you go. Okay, so this is just a little trick. This is definitely math trickeration to make it work when it doesn't work the way we want it. So just a little bit more about Green's theorem, some of the fun stuff that we can do. The fun stuff we can do to get around these issues. Okay, so it doesn't actually have to be simply connected. As long as it's got a finite number of holes in the region, you can still use Green's theorem. And that's basically what we did here to get around a problem spot. All right, so any questions on that one?
No, but I think that was like the perfect example to check to see if it's conservative or not before you do anything.
Yep, totally. Because I mean, it looks big and ugly and nasty, right? And it would have been even, I mean, even with the parameterization, like the circle is nice parameterization. But if it was some other thing, way faster to go, oh, hey, look, it's 0, right? The Py is equal to Qx, boom, you're done. So that's why I always do that first. Because if it's conservative, I'm done. If it's not conservative, well, I've got the partials I need to subtract for Green's theorem anyway. So it's one of the few times where I will do work that could potentially be extraneous work, right? Because maybe Green's theorem doesn't apply, but still, or Green's theorem may not be easier, but I'm still going to check those partials. Oh God, I'm going to check them.
So Bruce,
Yes.
In this example we just went over, would the question just be find the line integral of C?
Yeah, that would have been the question that we were trying to answer, was what is the line integral over that curve?
And we found, wait, so I'm confused how C is equal, the line integral of C is equal to the line integral of C1.
Okay, so this came from the line integral of C was, well, so the double integral, if we use Green's theorem on that region, like region with the hole cut out.
Oh, okay. Yep, I got it. The double integral is, yeah, okay, I get
The
it.
double
Yep.
integral was the difference in those two.
And since the double integral is 0.
There it is.
Gotcha.
Yep. Okay, so Victor, you just said, so we can let the inside surface be anything that includes the point. That's the problem. Yeah, we could have made that curve a square. We could have made it a triangle. We could have made it an ellipse. We could have made it anything we wanted. But we want it to be a shape that's easy to parameterize so that we can do the line integral quickly, or well, I mean, just so that we can do the line integral. I chose a circle because circles are easy to parameterize. We've done them a million times. And circles are only going to require one integral, as opposed to like if I had done a square, I would have had to do a line integral for each of the sides. So, but yes, it could have been any shape we wanted, any closed curve that we wanted that still contained the problem spot. Is that cool? Make sense? All right, awesome. Okay, so just some fun things you can do with Green's theorem. Now, let me show you some other properties of vector fields. Some things that we talk about with them that are going to be useful a little bit later on. They're also actually useful on their own regard. But these are called divergence and curl. Okay, so we've got the divergence of a field. So we'll start with this one. All right, so divergence of a field. We write this, there are a couple different ways you'll see it. The first is div of f. Okay, so this is saying find the divergence of f. And divergence is a number. Well, it's a scalar. It's a scalar. It can be a function. It can definitely depend on points. In fact, usually when we talk about the divergence of a field, it's not constant. The divergence will change depending upon where we are. But you're used to that, right? Like think about curvature. Curvature wasn't the same at every point, depended on where you were. Well, divergence of a field, same thing, okay? But it is a scalar. So divergence, you'll sometimes see it written like this. You'll also sometimes see it written as this guy del. I don't know if you remember that guy del from like the gradient. Well, this isn't saying this is the gradient of f. I tried to make it very clear that there's a dot there. So this would be del, that's the name we call that thing, del dot f. Okay, so if you ever see that, it means the same thing. I will try not to use this because it's really easy to use to get this notation confused with the gradient. So I will pretty much always write div. But if you ever see this del dotted with f, it also means divergence. Okay, so this is the notation. This is what tells you you're going to find divergence. All right, so here's how you do it. It's actually a really easy calculation. If f is equal to, and I'll try to use theirs again, so we'll call it PQR, then the divergence of f is equal to px plus qy plus rz. So you just take the three partials, you take them in order, first one with respect to x, then y, then z, and you add them up. Talk about easy. This is nothing. This is
Why is
absolutely
it not become a vector quantity? Is it because it's dotted?
okay. So, well, it's not a vector quantity because these are just partial derivatives. So these are just functions, just regular old functions that are being added together. So it's not a vector. It's just a scalar. You can think of it as a dot product, and that's why actually this notation comes about. If you think about del, the del operator, like when you do a gradient, remember what you're doing is you're taking partials with respect to x, y, z, like the gradient, here you go. The gradient of f would have been the vector that's formed by those. The divergence is the sum of those components. So you can think of it as the divergence is the sum of the components of the gradient, if you'd like. But it's not a vector because it's a different thing. We're just adding up components. But that's where this like dot, this del dot f notation even comes from, is you can kind of think of the del operator as a dx, dy, dz, right? You're taking the derivative with respect to x of p, the derivative with respect to y of q, z of r, for the gradient. And so for the divergence, we're taking that and we're dotting it with f. And that's what gives us the px plus qy plus rz. So it's not really a dot product. Not really a dot product, because this is not a vector. It's just saying we're going to take derivatives with respect to these things. And the dot would suggest we add it together. So it's not a dot product, but it acts like a dot product, which is why you'll sometimes see that notation. So basically, if you can find the gradient of a field, you can find the divergence. Because all you got to do is take those vector components and add them up instead of just writing them as the components of the vector. So these are really easy. It's not that hard of a thing to calculate. I mean, we definitely need to talk about what it means, but the divergence itself is easy to do. So let me show you an example. Let's say we had this vector field. It's x minus 3y, x squared, z squared, and xyz. Okay, so there's a three-dimensional vector field. If we want to find the divergence, here's all you do. You differentiate the first one with respect to x. That's 1. The second one with respect to y. That's 0. Third one with respect to z. xy. So the divergence of this field is 1 plus xy. So depending upon where you are, you'll get a different divergence, but that's the divergence in general. So like if we were at the point, say 1, 0, 0, you plug in 1 for x, 0 for y, 0 for z, boom, and that'll get you your divergence there, and so on and so forth. All right, so I've only given you one example, and I really feel like that's the only example I need to show you of divergence. Does that feel accurate? Like, we see what's going on here?
Yeah.
What is the significance of divergence? Sorry, I cut out.
No, that's all good.
Yeah, that's my question too. So like, what is it?
Man, you mean I gotta actually explain it to you now?
Dude, you're talking to a physics major.
I so wasn't gonna anyway. No, of course, yeah, like it's easy to do, but what the hell does it mean, right? What is divergence a measure of? Okay, so because of who I am, I'm going to talk about flow of water. Okay, so all of my examples, I always think of these things as fluid fields. All right, so we can translate them to other kinds of fields, but I'm going to give it to you in like fluid language. Okay, so divergence is a measure of flow. It's a measure of basically flow in minus flow out. Sort of like flux. Remember when we were talking about flux and flux over a surface or a curve? Divergence is sort of the same idea, except locally at a point. Okay, so for example, let's say that this is our flow. And we said, all right, well, what's the divergence at, say, the point 1, 1, 1? Okay, so we're going to go to the point 1, 1, 1 in space. We're going to calculate its divergence. And so in this case, it'll be 1 plus 1 times 1, which is 2. So what that would tell me as a fluid physicist is that at that point, more stuff is flowing out than coming in. I'm getting a flow of 2 at that point, a net flow of 2, a positive 2, meaning it's flowing out. If that divergence had been negative, more is coming in than going out. If it was 0, the same amount coming in is going out. So it basically, not basically, but it is the local measurement of flow at that point. So if we were talking about, let's say, this is an electric field. An electric field, this would be saying that there's like movement of charge, right, is what an electric field is, that there is movement of charge at this point, that more charge is going out than coming in. And depending upon which way we want to make positive or negative charge go, it's a little bit more.
the sign issues you got to watch for something like an electric field as opposed to like a fluid field. Okay, but that's what divergence is. It's local at this point, what's going on with my flow. So maybe it's the flowness of a field. Yeah, what the hell, let's make that a word. It's the divergence of F is the flowness of the field. It's a measure of the flowness. That feels wrong saying that word, by the way. Okay, so are we all right with what it's saying then?
Definitely.
Yeah. So I will just tell you that again, in like a fluid, like in a liquid, a water fluid situation, this would not be a field that we have for flow of water. Because flow of water, since water is incompressible, whatever comes in has to go out. You have to get 0 all the time. So hey, you guys remember source-free fields from last time? They were the ones that no matter what our closed curve is, we get a flux of 0. Well, for a source-free field, you're going to see the divergence is 0 everywhere. So anyway, so there's divergence. Super easy. It's going to be useful for other things, though, beyond just what it is. What it is nice. I mean, it does tell us the flowness of a point, but we are going to use it for other things later. Okay. So there's your divergence. All right. So then there's also curl. So we've got the curl of a field, and you will see this written as curl of F. Very creative, curl of F. But you will also see it with the del operator, but this time instead of a dot, you'll see it as a del cross F. All right, so this is one that I will write regularly, by the way. I will write del cross F because it's not something that you're going to get confused with gradient because of the cross symbol there. And it's really, really helpful in terms of remembering how to actually get the curl of a vector field. Now, the result of this is a vector. So the divergence was a scalar, but the curl is a vector. Now, if our F is PQR, then this is how you get the curl. So the curl of F, it's going to equal, and give me a second here because I got to translate this in my head. So it's going to be Ry minus QZ. And then we're going to get PZ minus RX. And then we're going to get QY minus, no, sorry, QX minus PY. And I think
cross products. Sorry. How many cross products do you have to do before you can do that intuitively without writing out the matrices?
I'm going to guess in my lifetime I've literally written out thousands of them. So somewhere between 0 and 1,000.
All right.
So yeah, I think for everybody it's different. But to be honest, I still visualize it in my head. Actually, in my mind, I picture all the going down the diagonal stuff. So, all right, so this one is rough to try to remember, unlike divergence. I mean, that's why I start with divergence, because divergence is nice. But curl, this is where the cross product thing helps you see it. Go to your cross product idea where we have I, j, and k. And then we have dx, dy, dz. And then pqr. And notice that what we get here are the components of this cross product. So think about the I. You're going to get dy times r, so you need an ry. And then you're going to get minus dz and q, so minus qz. That's our ry minus qz. When you go to the j, dz and p, so pz, minus dx and r, so minus rx. And then when we go to the k, we get dx and q, so qx minus py. So honestly, that's why I like writing the del cross f, because it helps me remember how to set this sucker up. All right, now finding curl is much more complicated, for sure, right? However, it's still very doable. So let's find the curl of this guy up here. So we found its divergence was 1 plus xy. But let's see what its curl is. All right, so we're still going to take all of those differentials. This time, though, instead of adding them up, we're going to go ahead and create this vector and see what it gives us. All right, so here's your curl. All right, so for the first component, we need ry minus qz. So ry was xz. And then qz, that's this guy, was a 2x squared z. All right, so that's the first component. The second component, we need pz. Well, this guy, when we differentiate with respect to z, gives us 0. Minus rx. Well, rx is yz. So it's 0 minus yz. And then the last one, we do qx minus py. So qx is 2xz squared minus py. Well, it's a -3, so plus 3. So the curl of this field is xz minus 2x squared z minus yz 2xz squared plus 3. And boom, just like that, we've got the curl of the field. All right, so like I said, this is a little bit more complicated than the divergence, but no, you can find it. Just a process of banging it out. So let me guess. What does this have to do with anything? What does it really mean? Yeah, all right, so here you go. So what is curl telling you? Well, you're gonna love this, because what does curl make you think, the name or the word curl?
Exactly
Like
what it
bending
sounds
or
like.
yeah, curling.
Curvature, bending,
Yeah.
right? Curling. So, okay, so curl gives you this kind of thought of, curving, rotating, whatever. Well, that's what curl of a field is. It's a measure of rotation. It's a measure of
if I were to give you a number, a point, let's say, okay, let's find the curl at the origin, let's say. What that vector is going to tell you is, does this thing want to rotate? If you get a curl of 0, that vector is 0. That means that the flow doesn't rotate at that point. So imagine we had a vector field that was, we'll go two-dimensional. I know I did this as 3D, but we can do them as 2D as well. But imagine that you had a vector field that was just like constant. Okay, so all these vectors point in the same direction. They're all the same magnitude. So imagine you were to put something in there that's maybe not a point, because trying to see a point turn would be a little bit harder, but let's say we drop in like a stick. So think about water, go to your favorite stream, lake, pond, whatever, and you drop a stick on top of it. It's going to follow the flow, right? If that stick doesn't rotate, that means there's 0 curl. So this would be an example of a field that has no curl, because you drop something in there and it'll move, but it's not going to curl, not going to rotate. We could easily make this so that it would rotate. So let me just adjust this slightly. So let's say this look like that. Now, if I were to drop something in here, it is going to rotate, because this end down at the bottom is going to feel a greater force pushing it than this one. So it's going to want to do this. It's going to want to rotate. So this is an example of a field where we would have curl, at least in this portion of the field. I mean, I don't know what's going on out here, but there'd be an example of one where we get some curl. The one I showed you of constant vectors, it's not the only one where you don't get curl. You can have ones that are not constant vectors where you still don't get curl. A good example of that would be something like this. Nope, check that. That's actually going to have quite a bit of curl. Hold on, how do I need this to go? I need the up vectors to have other up. Oh yeah, okay, there we go. So think about this one. If I put this in, I were to drop it down, it's still not going to curl, because even though, say, the end here on the left wants to really rotate, the part on the very right also wants to rotate, but the opposite direction, so it kind of gets balanced out. For you physics folks, think just like, torque. It's like we're balancing torques, so we don't get any kind of rotation. Anyway, so that's what curl is. It's a measure of rotation, just like it sounds like. So if you get a field where the curl is 0, that just means at that point, or maybe everywhere, there's not going to be curl. There's not going to be rotation. It's just going to flow. Okay, so divergence is a measure of flow. Curl is a measure of rotation. But before we kind of move on, we do need to address something here. I did this for 3 dimensions, for both of them, right? Like we did an example that was 3 dimension. What if our field is 2D? Are we still good? So Victor just said no pretty quickly in the chat box. What's the problem if it's 2D? Oh, there you go. So Victor already said, so the cross product doesn't work, right? We don't have this formula of the P's, Q's, and R's. Is there a problem with divergence if it's 2D?
No.
No, not at all. The definition of divergence is good, whether we're two-dimensional or three-dimensional. But curl, we definitely have to worry about it. So if you are three-dimensional, if you're two-dimensional, and you still want to do curl, basically what you've got is PQ0. There is no component of the field in the z direction, so that guy's just 0. Well, check out what happens. So all of the things that have r's are now 0. Yeah, right? Because there is nothing there, so the partials would be 0. So this is going to be a 0. This is going to be a 0. And also, all of the partials that have anything to do with z are 0. Because there are no z's anywhere if it's two-dimensional. So the QZ is 0, the PZ is 0. And so we can still get curl. Just in 2 dimensions, it's going to be 0, 0, QX minus PY. So the curl is always going to be pointing in the z direction. But there it is. And its magnitude is going to be QX minus PY. So I'm curious, for those of you who had physics with me last quarter, did this just like bring something back? Thinking rotation? I'm just curious.
Yeah, doesn't centripetal force always point orthogonal to the torque?
Okay, so not the centrifugal force, but you're on the right track. Places where we saw this with like angular momentum or even torque itself. Think about torque. We were looking at torque was a cross product of the lever arm and the force, but the torque was always orthogonal to the rotation. So was angular momentum, right? L, big L. That was always orthogonal to the plane of rotation. It's not coincidence that curl is also orthogonal to the plane that holds the field. They're all connected. They're all one and the same. I mean, if you want to think about it, when we did that angular stuff, we were really looking at curl. We just weren't in a vector field. Okay, so there's so many relationships between these that it's not even funny. But that's why we're seeing this thing that is three-dimensional, but it's orthogonal to the plane that we're in. All right, so you can still do curl for 2D. In fact, it's a lot easier. It's way fast, right? It's just 0, 0, QX minus PY. Huh. QX minus PY, where have we seen that before? You recognize that? Yeah, that was in Green's theorem. What the what? Oh man. Okay, so everything's really getting combined here. So it seems like Green's theorem has something to do with curl. What? All right, so it's kind of crazy. It's kind of crazy. But we can actually relate this stuff, curl and divergence, back to what we were talking about before.
That makes sense. Because
Conservative fields and Green's theorem and all that. So I'm sorry, Bradley, you just said what? It kind of makes sense?
so yeah, that kind of makes sense, especially when I think about like when we were doing Green's theorem on like things going along a path that were somewhat circular. There was curvature associated with it, and we were moving along that. Makes sense.
Yeah.
And
Okay, so check this out. Let's kind of rewrite some of the Green's theorem stuff we saw before. but we can now write them in terms of like curl and divergence. Okay, so we go back to Green's theorem. And there were multiple forms, right? So let's just go back to the work form first. So Green's theorem, we're integrating over our closed path, f dot TDS. And we saw that that was the same as the double integral over the region of qx minus by. So how could we write that in terms of curl and divergence? Well, it's not exactly just the curl, because the curl was a vector. So we can do this in one of two ways. We could write it as the integral of the magnitude of the curl of f, because the magnitude of this thing is going to give us qx minus by. Or alternatively, we can think of it as the curl of f dotted with the unit vector k. Because if we were to take this vector and dot it with k, it would just give us that. I like to think of it as the magnitude one. So this is what I recommend that you remember if you want to think of it, Green's theorem in terms of these other things. You get the curl of f is magnitude. So that was the work form. But also think about the flux form. So the flux form was f dotted with n ds. And do you remember how you do that? It's okay if you don't. I'm just curious.
Find little n.
Okay, so we found the little n and all that, but then when we generalized it, yep, thanks, Victor. We saw that it was the double integral over the region. Whoops, double integral, not double integral. Px plus qy. That came from the swapping. That's why the p and the q swapped, and then changing the sign. All right, well, if you notice, and you may not notice, so I'll just go ahead and show this to you. That's the divergence of f. Two-dimensional, right? Because remember, when we did Green's theorem, it's only for a two-dimensional world. So if we look at the two dimensions, it's actually the flux integral is the same as the double integral of the divergence over this region. This is why we still care about divergence and curl, even if we're not really looking at how much does this thing curve. What is the flowness of the field? Even if that's not what we care about, divergence and curl can be useful when it comes to just plain old doing Green's theorem. And let's go one step further. You remember conservative. You remember, and you remember source-free fields, or at least that they exist. Now I want you to think about what we know about them. Conservative. What's kind of the big deal about conservative vector fields? What do we like about them a lot? In terms of like line integrals and stuff?
Generally, they're pretty easy.
They're generally pretty easy. they're super easy if they're closed, right?
It's just equal to 0 if they're closed.
Because we know if they're closed, it's just equal to 0. Like the path doesn't matter. You can do the f of b minus f of a, but on these closed things, it just equals 0. Well, do you remember what the check was for conservative? What did we do?
Partials.
So you look at the partials, and specifically, which ones did you look at for a 2D field?
Isn't it py and qx?
Okay, py and qx, and they ended up equaling each other, right? Well, check that out. So we can see that here. If qx and py are the same, then this is 0. What does that mean for the curl?
It should be 0 as well.
Yeah, it's 0. So here's actually the check for conservative fields. Okay, so f is conservative if and only if the curl of f is the 0 vector. Now, you probably have done enough playing around with the 2D ones that you're getting comfortable with the qx minus py. But think about the 3D ones and that like cross partials check at those 3 different sets of partials that you had to see if they were equal to each other. Those were the 3 components of the curl. I was playing this, I was holding this one pretty close to the vest. But it turns out this is actually the check for conservative. You go and you see, is your curl equal to 0? If the curl is 0, then it's a conservative field. Done. Okay, well, we can actually look at something similar for the ones that were source-free, right? The source-free fields, these were the guys where the flux integral over a closed path always equaled 0, which meant the px plus qy always equaled 0, which meant the divergence equals 0. So we can say this. F is source-free if and only if the divergence of f is 0. And just drawing your attention on not putting an arrow over the 0, because that's not the 0 vector, that's the 0 scalar, where the curl was the 0 vector. So these give us really quick, really easy checks for both conservative and source-free. So basically, this is why we still care about curl and divergence, is for these checks. So if you look at like gravity, if you look at a gravitational field and you look at the 3-dimensional version of it, you will see that its curl is 0 always, no matter what the bodies are. So gravity is always conservative, right? You'll see that actually magnetic fields are always source-free. And I know that you guys are kind of like in the middle of magnetism right now, right? Or maybe you're kind of finishing it up in physics. But
yeah, we're in magnetism right now.
We're in magnetism.
Okay. So think about magnetism, how you can't have like a North Pole without a South Pole, right? Like I know that Bradley, you mentioned this the other day about how it's kind of cool if you break a magnet, all of a sudden it sort of creates new poles on those.
Yeah, it's so wild.
Okay. Well, that's because magnetic fields are source-free. In order to be source-free, if you're trying to isolate a positive, like if all you had was I'm going to call them positive and negative for north and south. So if all you had was a north, then there's going to be flow in and out. The south shows up to counteract that north, so that you don't end up getting flow in or out. It's source free. So the fact that magnetic fields are source free is why you see those pop up, or maybe vice versa, right? The fact that you always end up creating a south for every north makes it so magnetic fields are always source free. So if you go and you look at any magnetic field you've ever dealt with, check its divergence, and you'll see that its divergence is always 0. So this actually has huge use when you're dealing with stuff in physics, anytime you're dealing with field forces. All right, well, it looks like our time's up for today, at least if I'm reading my clock right. So kind of where we are, now that I've introduced you to divergence and curl, and even kind of given you a little bit of why we care about them, I'll show you, we're going to start seeing some more relationships between divergence and curl and some theorems. So our plan for the next little bit, I mean, we got 2 weeks basically. I'm going to introduce you to surface integrals, which are the same idea, integrating but over a surface. And then we're going to develop some theorems that relate to those. And I kind of already hinted at a 3D version of Green's theorem, right? And so we'll talk about that, and then we'll see another theorem that kind of ties it all together. So we're sort of at that climactic moment of the movie where everything you're going to go, oh man, this is how everything gets tied together, right? We're just about there, and you've been seeing glimpses of it, right? You've been seeing glimpses of the, oh wait, we just did this, right? And now we're going to call it this new thing. Well, we're going to continue that, and so this next 2 weeks, we're going to basically wrap it all up, tie it with a nice pretty bow, and put it under the Christmas tree. All right. So that's where we are. I'm going to remind you that there is going to be an exam next Friday. And I'll just go ahead and tell you, I don't remember exactly what sections everything was, but I kind of think the last test, wasn't that just basically chapter 5?
Yeah.
Okay, so this one's going to be chapter 6 up to and including the section on divergence and curl. So whatever section that is. We'll talk more about it next week, but if you want to start studying and preparing, just realize it's going to be chapter 6 up to and including what we did today. All right. So with that, I'm going to wish you all a great weekend and stop the recording.